Good afternoon, everyone, and welcome to the EOL seminar series. It's been several years in the making, but finally we were able to craft some free time in his schedule to bring him to the podium. It is my great pleasure to welcome our speaker, Dr. Britt Stevens. Dr. Stevens is a senior scientist at EOL's Research Aviation Facility. Britt received his PhD in oceanography from Scripps in California, and his postdoc was in the carbon cycle and greenhouse gases group at NOAA, when focused on field-based atmospheric oxygen measurements and the global carbon cycle. So now here at NCAR, Dr. Stevens has honed his research craft on building new instruments and adapting existing ones that he and other scientists can use to study the global carbon cycle. Britt has designed and built an airborne vacuum ultraviolet absorption O2 instrument, a tower and ship-based fuel cell O2 measurement system, a tower-based autonomous CO2 analyzer, and an airborne flask sampling system for laboratory measurements of O2, argon, and isotopologues of CO2. So with all these instruments, Britt has traveled all over the world on numerous ground, ship, and aircraft-based field campaigns, HIPPO, ORCAS, and ATOM, to name a few. Britt is currently leading the Southern Ocean Carbon Gas Observatory, or SCARGO. This is a multi-year NSF Polar Programs funded effort to measure CO2 and other gases from the C-130 aircraft flying in support of the US Antarctic Program. And SCARGO is the program that Britt is going to be talking about today. So for those of you online, welcome. If you have any questions, please ask them on the Slido screen at the bottom of the presentation. And we're going to be archiving your questions until the Q&A at the end of the seminar. Dr. Stevens, welcome, and the podium is yours.
Thank you, Jackie. Great to be here. I'm going to talk about this NSF Polar Programs funded project that I'm leading in collaboration with CGD, CU, and NOAA. We pronounce it SCARGO. That maybe was not a great idea because it's moved somewhat slowly, but we're sticking with it. I'd like to acknowledge my co-PIs, Matt Long and Catherine McCain, as well as the many people who contributed to making the field measurements possible last year, including Charlie Martin, who's here in the audience, Eric Morgan from Scripps, and Hannah Allen, who's now at LSCE, as well as a group of collaborators from New Zealand. I'd also like to thank Jesse Vance and Yuming Jin, who have done most of the analyses that I'll be showing today. Jesse is a postdoc formerly in CGD, although working both with Matt and myself on this project. And Yuming is a recent PhD from Scripps, who graduated a few weeks ago, or got his PhD a few weeks ago, and he'll be starting an ASP postdoc with us here in EOL in January. This is a picture from a beautiful day at Willie Field at McMurdo, just after Charlie, who's in the center there, and I arrived last November. The aircraft we were using are the skied C-130s that fly in support of the US Antarctic Program, and our goal is to measure CO2 and other gases in order to estimate air-sea CO2 exchange with the ocean around Antarctica. So here's a little bit better picture at that aircraft. It's similar to our C-130, except it has skis, which you can see here, that allow it to land at McMurdo in the middle of the summer when it's too soft for wheeled planes, and at South Pole, as well as deep field locations with unimproved runways. The other big difference to our C-130 is it's a cargo operation. As you can see here, they're loading stuff in the back, and that makes a huge difference working on a research aircraft versus a cargo plane in terms of how you integrate instruments and how you work in with the rest of the operations. So I'll touch on that later. We're really just getting this project off the ground, having done a test deployment last November and December. So a large part of my talk will be presenting the scientific context that motivates this work, as well as some of the methodological developments we've made over the past few years. That'll be about the first half of the talk, and then the second half of the talk, we'll get into what we've actually done as part of this project. A quick outline here, which I just briefly mentioned. I'll cover sort of the state of the science, some of the observational challenges, what we've done in the past with aircraft over the Southern Ocean. It turns out they're uniquely powerful at ascertaining air-sea CO2 exchange. But you can imagine there are a lot of methodological choices. The aircraft measures CO2 concentrations, and we want to know what the air-sea flux is. So how you get from from the concentrations to the fluxes is a big area of research. And then in terms of what we did over the past few years, the development, the test season, the preliminary science results, and future outlook. So the Southern Ocean is an important part of the climate system because that's an area where the deep ocean is able to exchange heat and carbon dioxide with the atmosphere. The geographers define it now officially as the ocean south of 60 south, but oceanographers use a range of latitudes, and one of the most common is sort of south of 45 south, and that's what I'll be presenting here. The Southern Ocean is an important sink for anthropogenic CO2 that's produced from fossil fuel burning or burning down rainforests. And we know from hydrographic sections that about 40% of the CO2 that we have emitted and is now stored in the ocean entered through the Southern Ocean. And that's really because of this chemical equilibration process, just like the CO2 that's dissolved in a can of Coke. It's an equilibrium. We're increasing the amount of CO2 in the atmosphere, and so that's slowly evading the ocean. The deep water around Antarctica hasn't seen that atmospheric increase before, so when it comes up, it's able to absorb a lot of it. But it's really hard to measure for a number of reasons, one of which is all the other processes that affect CO2 going in and out of the ocean. So one thing that happens when that water comes up, it's typically warmer than the air. So when it cools off, the solubility increases, and so it can absorb more CO2 from the air. If that water flows north, it warms, and the opposite happens. The solubility decreases, and CO2 wants to come out. And then on top of that, that deep water that's coming up has accumulated all of this biological carbon sinking algae for hundreds of years, which have then decomposed. There's actually a lot of dissolved CO2 in that deep water. So when it comes up, there's a biological respiration signal, CO2 wanting to come out. And then that water also has a lot of nutrients in it that also went down with all the sinking organic matter. And when that comes up, it tends to drive photosynthesis. So you have these opposing thermal and biological drivers on top of the anthropogenic uptake. And so that's one reason it's hard to sort all this out. But we really do want to measure these fluxes and the processes so that we can say what they might do in the future. There's speculation that increased winds over the Southern Ocean might accelerate this upwelling, but then the impact of that on all these different arrows is very uncertain. There are other reasons why it's a hard thing to measure. Number one, it's highly variable. This is a satellite image showing the average chlorophyll during summer over about 11 years. So you see a lot of variability, even though it's an average picture, driven by regions of the ocean that experience more upwelling during summer and bringing nutrients up in different spots. So you can imagine trying to take a ship or a robotic float to some spot in the ocean, and what you measure would depend more on where you actually happen to be than the large-scale exchange that we're interested in. On top of that, it's really remote from places where people have research institutions or labs, and it's pretty inhospitable. Anybody who's ridden across the Drake Passage on a ship, I know Allison is one of those people, can tell you it's not really the kind of place most people want to hang out for much time. So there are a lot of reasons why we don't know very much about the Southern Ocean. The ways that we have estimated the uptake of CO2 include, measuring the dissolved CO2 concentration in surface waters, or the PCO2. And the map on the left is showing all of the PCO2 measurements collected from 1957 till essentially today by a community data synthesis effort called SOCAT, the Surface Ocean CO2 Atlas. And you can see CO2 is higher along the equator in the Pacific, where you have upwelling, sort of more shallow upwelling of CO2-rich waters, and it's low in the North Atlantic, where waters are cooling and sinking. And if you just look at this big picture, it looks like we have pretty good coverage over the Southern Ocean. But the map on the right is what you get typically from 1 year. And so you can see there's really not great coverage over the Southern Ocean. Most of the measurements made south of about 45 South are made on the Gould, which is a ship supporting the Antarctic Program. That's a picture of the ship. To the left of it is an equilibrator. That's the device that measures PCO2. So you spray water and pull air through, and they equilibrate, and then you measure the CO2 in the air. So that you can get numbers from this approach by taking the difference in PCO2 between the water and the air and multiplying it by a gas exchange coefficient, and that gas exchange coefficient is parameterized as a function of wind speed. So the limitations are that the measurements are sparse in space and time, and the number you get is dependent upon this K term, which also has a lot of uncertainty. Another popular method is to use measurements in the atmosphere of CO2, primarily from surface stations, either collecting flasks and sending them back to labs or measuring continuously, and then doing what's called a 3D atmospheric inverse estimate. You can imagine forcing an atmospheric transport model with a lower boundary condition of fluxes and then observing where the winds blew that CO2 around and trying to predict what the CO2 concentration was at a station. This essentially does that in reverse. It takes the CO2 concentrations measured at stations and given the winds, tries to infer what the fluxes must have been to produce those observations. That's why it's called an inverse calculation. And there are various methods from sort of matrix-based Bayesian synthesis inversions or data assimilation techniques like ensemble Kalman filters or 40 VAR. A lot of groups around the world are doing this, and you can get estimates for the Southern Ocean. But again, these are limited because of the sparse nature of the sampling network at high southern latitudes, but also that most of these measurements are from the surface for stations at low altitude. And so we're really dependent on the atmospheric transport models telling us what the vertical mixing is, and that's something they have a hard time doing. So if you look at the some recent estimates of the uptake of CO2. On the left is something from the Global Carbon Project, which is a big effort that puts out a synthesis every year of our best estimates of carbon fluxes. This is for the ocean south of 30 South. And you can see for the PCO2 measurements kind of in this teal, and then for the inversions in the purple. It looked like the uptake was sort of decreasing, so these are negative numbers, meaning uptake by the ocean, and then it's accelerated. There was a notable paper around 2007 that was predicting that given the acceleration of winds, the CO2 uptake should be slowing down and might continue to do so, but then that all of a sudden, right after the paper was published, reversed. We now think that a large part of this was cooling due to Pinatubo. And the overall increase in the flux is because the atmosphere, again, is increasing its CO2 concentration, and this deep water is essentially the same concentration it's had for a long time. But the black line being Earth system models, the teal line being the PCO2 estimates, and the purple line disagree. And then you can see the shading is sort of the one standard deviation of all of the different models or flux products they used, and those bands are quite large. This is just in terms of the mean flux and the trends. If you look at the seasonal cycle, it gets even messier. This is a collection of atmospheric inverse models and PCO2 products estimating the exchange of CO2 south of 45 South over the course of the year. And there's quite a lot of divergence. If you just look in summer, so December, January, and February, there's probably a factor of 2 or more difference in the predicted uptake, and then in winter you either get no uptake or slight outgassing, or quite a lot of uptake. So it would be fair to say we really have no idea what the CO2 exchange is with the Southern Ocean. We have uncertainty on the means, the trends, the interannual variability, and the seasonality, and that all prevents us from understanding the processes well enough to make a prediction. So how are we going to, how can we fix this problem of not having a good handle observationally on this important climate process? Well, one of the first clues we got was during the HIPPO project way back in 2009 to 2011. So this was a series of global campaigns on the G5. It was led by Harvard, Scripps, NCAR, and NOAA. We did 5 campaigns over 3 years where we flew circuits like this shown in the top right for HIPPO 1. HIPPO 1 was in January, so this is winter in the north, summer in the south. And this cross section here, which shows all of the flight tracks, we went up and down the whole time, mapping out the two-dimensional distribution. It shows high CO2 in the north from fossil fuel burning and respiration during winter. And that's sort of what grabs your eye. But if you look more closely over Antarctica, you see shading from blue to purple, something like a 2 part per million gradient with lower concentrations at high latitudes and low altitudes. And this is reflecting uptake of CO2 by the Southern Ocean. So we started staring at this in 2009, but it took about 5 or 6 years before Matt Long and I decided that, hey, we should go back and spend some more time down there, not just one day, and really measure the system. And then we also wanted to measure oxygen and other gases to really inform on the processes. So we wrote a proposal in about 2014 to take the G5 back down to Punta Arenas, and that was funded. The project was called ORCA's, O2N2 ratio and CO2 airborne Southern Ocean study. This is a satellite map of chlorophyll during the time of the campaign, which was in January and February of 2016, with the flight tracks overlaying. Typically, we would fly out of Punta Arenas at high altitudes and transit to the productive coastal regions of the Antarctic Peninsula and do some low-level profiling, and then fly back doing these sort of large-scale cross-sections. I'm not going to talk about the oxygen. It was really valuable in getting at the biogeochemical processes, but I'm just going to focus on the CO2 during this talk. This is what we saw, again, in a cross-section, altitude versus latitude. The panel in the top right is the actual flight tracks, just colored by flight day. You can see we really, over 6 weeks, oversampled the domain, and if you bin all of the data and average it, you get this cross-section with higher CO2 in red and lower CO2 in green. The concentrations have been detrended, so they have a reference of 0. And this, the green to red shading here is showing you this huge drawdown signal over the Southern Ocean. We had members of the science team, co-PIs, who were predicting we weren't going to see any gradients in CO2 based on some earlier model runs we'd done using PCO2 data as input. So when we saw this huge drawdown, that was really eye-opening. Another thing shown here are lines of potential temperature in gray, and you can kind of see that the gradients follow potential temperature, and that's because the atmosphere mixes preferentially on surfaces of constant density. So the rate-limiting step in terms of mixing air is diabatic mixing across those surfaces. So this was a really, big deal when we saw this, that CO2 uptake was a lot more than we thought during that time. And we started setting about putting it in the context of other measurements and understanding. But at the same time, NSF had funded this new project to deploy robotic floats around the Southern Ocean called SOCOM, the Southern Ocean Carbon Climates Observations and Modeling Project. And they've now put something like 250 floats in. At that time, they had maybe around 100 floats in. And what those floats don't measure PCO2, but they measure pH. And from pH, you can infer PCO2. And those calculations led them to conclude that there was a large outgassing of CO2 from the Southern Ocean that was in contrast to what we'd been expecting. So this was a little news story in EO saying that the ship measurements were overestimating the sink. This is what that result looks like. With the float estimate, this is for annual mean air-sea flux of CO2. So the brown lines are based on PCO2 measurements, including the float data. And the tallest one is if you only use the float data. The others are if you use a combination of shipboard and float data. The blue is the PCO2 from ships. The white are estimates from inversion. So the theory at the time was that, well, maybe the ships are missing some region of the Southern Ocean that's important for releasing CO2, and maybe the inversions are missing a big sink of CO2 on land that would somehow, counter this large outgassing. But this, gave more sort of import to our interpretation of the ORCA's results. So we took our time. We brought in measurements from other airborne campaigns and a whole bunch of models. And what we ended up doing was developing an emergent constraint approach. These plots are showing vertical gradients, fluxes plotted against vertical gradients for a bunch of different atmospheric transport simulations. So each dot is the result of an atmospheric transport model run forwards with different fluxes of CO2 producing different gradients in the atmosphere. The vertical gradient is actually calculated across potential temperature bins, as shown there on the right. And the fluxes are average south of 45 south. So it's what you expect, a model that has more uptake, so more negative concentration gradients in the atmosphere, also has more negative, or fluxes or more uptake. So more uptake, lower CO2 near the surface, less uptake, more CO2 near the surface. And then the slope tells you something about the sensitivity of the measurement. The vertical lines here are what were inferred from the ORCA's measurements in January and the ATOM-2 measurements, that's ATOM-1. So ATOM was a sort of a follow-on to HIPPO that ran on the NASA DC-8 from 2016 to 2018 and measured many more reactive species. So using these three campaigns, or series of campaigns, HIPPO, ORCA's, and ATOM, and 13 atmospheric transport models, we're able to infer a flux from the intersection of those two lines in each plot. The gray dots represent all of the summer, all the measurements in that season from all campaigns, whereas the colored dots on the left, in this case, are from ORCA's, and the colored symbols on the right are from corresponding to ATOM-1. We also tried to do this from surface station data, and it's so this is now, the x-axis has been replaced with the gradient between stations over the Southern Ocean and the South Pole, and it sort of works in summer. On the left, you get a relationship. On the right, in winter, it doesn't really work. The way the storms mix the air over the Southern Ocean, it sort of wipes out any gradients. And if you look at the slopes here, the slope on the top in summer is about 1 petagram per ppm. So what that tells you is it takes a petagram of CO2 coming out of the Southern Ocean to produce a ppm gradient. Whereas down here, the slope is 5. It takes 5 petagrams of carbon to produce a ppm gradient. So what that's telling you is that the vertical gradient is 5 times more sensitive to the fluxes than the horizontal gradient. And that, again, is just because of how the atmosphere mixes. So it mixes rapidly horizontally with synoptic storm systems, but diabatically or vertically, it mixes much more slowly. So the aircraft are more sensitive at getting at the flux. This is what those results look like. The black dots are now the intercepts from all of the points from all of those campaigns, and the black line is a sort of a harmonic fit to those. And this is the same seasonal cycle plot I showed before, but now it has brown symbols added for these float-based estimates, with the brown squares being the float-only estimate. So we got a seasonal cycle that looked somewhat similar to previous estimates, but was at the low end of almost all of them. And an annual mean, it ended up giving an uptake flux that was, again, stronger than all the other previous estimates. So, this was a really nice result to be able to demonstrate that we can see this from the air, but there were a couple limitations. Key ones being that we're only able to estimate fluxes for this huge region south of 45 south. Another being that we're dependent on running something like 13 atmospheric transport models over all these different fluxes. It took a large group of collaborators to achieve that. And then the other limitation is that we're dependent on the atmospheric mixing in those transport models. So if on average those models all get too much mixing, then our flux result would be biased. So Yuming Jin, working with Ralph Keeling at Scripps, set about improving upon this technique. And in a previous paper, he had introduced a new coordinate system for the atmosphere based on mass integrated over potential temperature surfaces. And then he adapted that to produce a box model for the Southern Ocean. So what's shown here is a box model where the divisions between the boxes are potential temperature surfaces. So they're lines of equivalent potential, constant equivalent potential temperature, but it's integrated from the poles such that each box has exactly the same mass. In this case, 15 times 10 to the 16 kilograms. So if you did a box model like this just with potential temperature surfaces, they would move around over the course of the season as the hemisphere warms and cools. But by setting them to have the constant mass underneath them, they essentially stay in place. So it's this really nice framework for calculating integral quantities in the atmosphere and doing box model calculations. Another benefit is that, so the key thing in the model is what are these diabatic transport terms. Because the atmosphere tends to mix along the surfaces, it's really this rate limiting transport that matters. And Yuming showed that you can estimate these from reanalyses, so you don't need a coarse resolution atmospheric inverse model to get them. So that's a really powerful advance. We do require still models to do a spatial bias correction because we tend to fly in at one longitude and we're trying to represent the whole zone. We use models to correct for that. However, because the winds blow so fast around Antarctica, the measurements anywhere tend to be fairly representative of the whole zone. So those corrections are manageable. The big benefits, again, are that we get more accurate transport and we can actually partition the fluxes into multiple latitude bands. This is showing those diabatic mixing terms, or the diabatic mixing term across what was the second line in the previous plot at 30 times 10 to the 16 kilograms. And the orange and yellow lines are what Yuming gets from reanalyses, and so those are in close agreement. And then the other lines are all what you get from these coarse resolution atmospheric transport models. So one thing that Yuming found was that those models are tending to overestimate mixing at summer, at summer and in winter, but at high southern latitudes. And that has implications for the result that Matt and others published in Science that I showed a few slides ago. So this is the result of applying that box model over the HIPPO, ORCAS, and ATOM data. And you can see you get fluxes for 3 different boxes, and then the one on the right is just the first 2 boxes added together. It resolves this really nice seasonal cycle at high southern latitudes. So this is showing uptake during summer, December, January, February, when the algae is photosynthesizing. At the next box up, you still see the same phase of the seasonal cycle. And then one of the really cool things about this result is that it can resolve the seasonal cycle flipping sign as you go further north. And that's because north of about 43 south, the ocean is no longer dominated by the biological processes, but is dominated by the thermal processes. So during summer, you have more outgassing because the water's warming rather than more ingassing because of photosynthesis. And then on the right is a comparison to the Long et al. Result, as showing that with this improved model, you get slightly less uptake. The annual mean number is something like 0.35 instead of 0.5. That's again because the models that were used in the Long et al. Study were overestimating the mixing. This is comparing to a whole bunch of other estimates. I just wanted to highlight the float-based estimate in light green here. The other nice thing about Yuming's result is we can see that the disagreement with the floats, which is shown for the region south of 43 south on the far right, is actually coming from south of 51 south, which is the region on the left. So that tells us, the floats seem to be okay north of about 51 south. So, okay. That's about it for the methodological stuff, but just to sum up, the aircraft offer distinct advantages over other methods, and among those are that the atmosphere integrates over all of that heterogeneity in the surface fluxes, and so what you get is this sort of average signal, representative of really large spatial domains, thousands of kilometers. By sampling the full column, you can overcome a lot of the uncertainty in vertical mixing. And as I mentioned, the vertical gradients are more sensitive to fluxes than the surface gradients. However, we only have a few campaigns, and they're really sparse in time. So we had 5 campaigns between 2009 and 2011, and 4 campaigns between 2016 and 2018 for hippo and ATOM, and then we went sort of in one concentrated effort for orcas. So we can only get this climatological picture, and what we really want to be able to do is to resolve the interannual variability as well as the subseasonal trends in the fluxes. So we realized after orcas that we wanted to figure out a way to do this more routinely, and the aircraft flying in support of the Antarctic Program provide a good way to do this. Okay, so I might not have mentioned, they're called the LC-130s, whereas the L designates the skis. They're operated by the New York Air National Guard in support of the Antarctic Program. And they do routine flights between Christchurch, McMurdo Station, and the Pole over the summer field season, which runs from the start of November until mid-February. So we weren't the first people to use these planes for science. The Rosetta Ice program ran from 2015 to 2018 and flew radar and gravimetric surveys of the Ross Ice Shelf, which is shown there southeast of McMurdo. And that was a very successful project. It used a lot of flight hours, and they had the plane all to themselves when they were doing their science. We're taking a slightly different approach and trying to piggyback along during routine cargo flights. So we wrote this again. I teamed up with Matt and Catherine, who were both co-PIs on orcas, to propose this effort. It was in the top right is a figure from our proposal showing, again, this cross-section, altitude, latitude, CO2 during summer, but from CESM. And these were the flight tracks that we envisioned we might get to do. Our program manager at the time had suggested we request these dedicated flights out of the Southern Ocean. It turns out they're a lot more expensive than just riding along on already planned flights. So it's unclear whether we will get those, but we're trying to make up for not having those with more frequent flying. So the primary goals of SCARGO are to measure the seasonal evolution of air-sea CO2 flux over the summer season, and then to measure the interannual variability. So to go back and do this 3 years in a row. And both of those things, but in particular the interannual variability, can serve as a laboratory for understanding processes. So if there's more or less uptake in one particular year, we can start to investigate with models why that might have been. We also have a third important goal, which is to demonstrate that we can do this from the routine flights. And if we're successful in doing that, that might lead to future proposals to keep going. So this project was funded. And as I mentioned, we went down last November. We didn't start working on the logo until we were actually out in the field. It's still a draft. We have to get some skis attached here to make it realistic. This is a picture of Charlie working on the instrument on our first flight from Christchurch down to McMurdo last November. And you can see that particular flight is for moving Air National Guard crew to and from the ice. So it's not a lot of cargo, but a lot of people and quite crowded. And I'll say more about the rack in a minute, but it mounts to the side of the aircraft out of the way of cargo operations. This is sort of the full timeline to date. We wrote the proposal in May of 2018, and we naively thought we would be out flying in November of 2019. The proposal was finally awarded in March of 2019. It only took us 2 months to get all of our paperwork in to the Air Force to get approval to put this on the plane. And then took 2.5 years to actually get that approval. It was partly a result, that long duration was partly a result of COVID, but it was also because, understandably, we're not a priority for the Air Force. They're, approving things more closely related to their mission. So we kind of got put on the back burner. But as soon as we got that approval, we did a set of test flights out of Schenectady, and then got our official approval for flight operations in about August, and then our test deployment was in November and December. So this is the rack we're using. It's made by a company called Airdyne, which sells these huge systems, robotic arms that attach to the back doors of C-130s. That's what was used in Rosetta ice, and we've actually test flown that on our C-130 at the request of Polar Programs. But we're just using the rack, the avionics rack that goes with it. And in that rack, you can see the items installed. The key one is a Picaro gas analyzer that measures not only CO2, but methane, CO, and water vapor. And we have calibration gases and other hardware. And this shows the rack rolls in on a hand truck and clips into the side of the plane. And this was sort of suggested to us as a way to be on the plane and not interfere with these large pallets of cargo that need to slide back and forth. The way we get our sample air is by replacing the forward escape hatch with a custom hatch. Another commercial company sells custom hatches for C-130s for putting antennas and other things on, and we got them to modify one to allow for air inlets, which you can see sort of zoomed in here. Not unlike something we would have flown on the C-130 back in the day, just a bare tube aft facing. And then because we're in the back of the plane, here's our rack. We have quite a long tubing run from that hatch. And then we also aren't allowed to interface with the plane, the navigation computer in any way. So we have to fly our own GPS antenna to know where we are. So there's a GPS antenna and a 1/8" stainless tube that run the length of the plane to our instrument. So here's a timeline of our test season. We initially thought we were going to get the full season, November through February. We were quite excited about that. The people who do the cargo operations on the ice weren't really fully engaged until quite late in the process, and they raised some concerns about impacts on what they were trying to achieve. So we got sort of de-scoped initially. And then later on down in the list here, we got following some unexpected COVID impacts on the overall program. We're de-scoped further. So we integrated in Christchurch following there was a pause. We were actually at the airport on our way. Charlie flew a day early, so he made it to Christchurch, and I got to San Francisco before they canceled all Antarctic travel for 2 weeks because of an outbreak at McMurdo. So I came home, went back a few weeks later, and we eventually got to go. And we did 8 flights over 5.5 weeks. Is that? And of those, there were 3 flights from Christchurch to McMurdo, 2 from McMurdo back to Christchurch. The instrument ended up on the ice and came back by ship. And then we did 3 round trips to the pole. And on one of them, we tested doing a vertical profile in the middle. So it was a successful test of operations. We were able to, really perfect getting the instrument on and off the plane. This is a picture of Hannah Allen riding along with the instrument on a sled that's being towed by a four-wheeler. We started out towing it across the ice ourselves, but Charlie took enough unflattering pictures of me towing this thing like a sled dog that we opted for a more glamorous route. And then in the background, you can see Mount Erebus and a tent, a nice warm tent where we were able to work when we weren't flying on the plane. So it was great from a science point of view and from an operations point of view, but we did identify some stresses to the cargo planning system that I'll touch on near the end of my talk. This is where we got to fly. Flights are colored by date, so there's a purple Christchurch and McMurdo you can't see because it's buried beneath the other points. And then we did the 3 trips to the pole, and then at the end we did 2 more trips back and forth to Christchurch. So it was not a very even distribution in time, and so for the analyses I'm going to show, we lumped all the flights from the entire campaign together. And you can see here, this is now in feet, so we can kind of talk to pilots, but the plane makes it to about 26,000 feet coming back from the South Pole, which is pretty good for a C-130. But when it's fully loaded, coming from Christchurch, it's only around 20,000 feet. These are all of the CO2 profiles we measured on the left over South Pole, in the middle over McMurdo, and on the right over Christchurch. So the first thing that jumps out is there's a lot more variability over Christchurch, and that's because of all of the local terrestrial sort of photosynthesis and fossil fuel burning signals that you experience there, either from New Zealand or from Australia, most likely. Once you get to McMurdo, the signal is a lot clearer, a lot less variability, and likewise at South Pole. And if you look, you kind of see this rightward lean to all of these profiles, so less CO2 near the surface. Actually, between McMurdo and South Pole, the lowest CO2 we measured was over the South Pole. There's no photosynthesis going on in the middle of Antarctica, so that's an ocean uptake signal that's been transported there. If you plot the same data just as colors on an altitude versus latitude plot, this is what you get. And you can see again these sort of darker blue colors at lower altitudes over McMurdo and Christchurch. And then the lines here, again, the divisions of this box model. And you can see that the southernmost box has blue colors, and the next box up is kind of a lighter green, and then yellows and reds as you proceed north. So Jesse Vance has been working on adapting the box model that Yu Ming developed and applied in a climatological framework to actually making estimates from our SCARGO measurements at the actual month or week of measurement. This is what it looks like to plot CO2 against this mass-based coordinate. So starting from the pole and going to the north, it's just each one of these ticks on the x-axis is essentially one of the boxes in that box model. Most of these plots are from Yu-Ming Jin's paper that's in review, showing all of the previous campaigns, and then the one on the right is a plot from Jesse for the SCARGO measurements. So you can see generally the plots all align low on the left, high on the right. The slope of what we saw in SCARGO is not too dissimilar from what we saw in ORCAs or ATOM-2 or HIPPO-1, which are also summertime campaigns. You can see the winter campaigns, HIPPO-5, HIPPO-4, ATOM-1, they're all more flat. If you look really closely, you can kind of see during SCARGO it levels off a little bit around 30 times 10 to the 16th kilograms. Likewise in HIPPO-1, that shows up once you calculate the fluxes. This is just a list of all the things that Jesse's kind of tweaked. The equation that gives you the flux from the box model is essentially the rate of change of mass within a particular box plus the transport terms across the surfaces north and south. And those transport terms are parameterized as a diffusivity times the CO2 gradient. So whereas Yu-Ming got the diffusivities from a climatological analysis of reanalyses, we're getting them from the actual time of sampling. As I mentioned, we're lumping the gradients for the full 7-week test season, but we hope during a regular season we'd be able to make estimates at monthly and even possibly weekly resolution. We're doing this same spatial bias correction. We're using the Carbon Tracker near real-time model, and we plan to add several other models that are available with short turnaround times. So we're from colleagues, so we're not sort of doing this thing we did in the long study of collecting 13 simulations. And then for the actual 2022 data, we're estimating the rate of change within the box from station data, and these plots on the bottom are just showing that works pretty well. The plot on the left is showing the predicted concentration rate of change from just using South Pole data, and then the actual 3D rate of change from the Carbon Tracker model. And on the right, the black and the colored are showing predicted versus actual. So this is evaluated in model space. It shows it works pretty well. In an El Nino year, 2016, CO2 is going up faster, but it's going up faster because it's going up faster everywhere, not because of something necessarily going on in the Southern Ocean. When we have a full season of flights, we'll actually use the airborne data themselves to define this rate of change term. And one of our goals is to be able to produce flux estimates fairly quickly after a campaign to feed back into other efforts that are pursuing sort of more near real-time or rapid turnaround estimates of carbon cycling. This is the results we get from that box model shown in red overlaying on the figure I showed previously. South of 51 South, our estimate aligns really well with the previous climatology. Between 51 and 43, it's actually a little bit above the line, and that's related to this sort of flattening of CO2 in the middle of the CO2 gradient in the middle of the domain. Hippo 1 is this dark blue plot. It was also a little bit above the line. So there's a little bit of a suggestion that at this latitudinal zone, there's more interannual variability in exchange. And so that's something we hope to explore more with 3 full seasons. And then putting it on the combined box on the right with the long et al. Study, it also aligns pretty well. A little bit above the line. These estimates are fairly preliminary. We're still working through some of the corrections and as well as the uncertainty budget, which is shown down here. The uncertainty budget includes terms related to the rate of change in the box, the diffusivity, the gradient, fossil fuel and land flux correction. But the largest of those is really the uncertainty in our ability to measure that gradient between 2 boxes, which itself depends on instrumental uncertainty and this sort of correction from measurements at one longitude to a box that spans the whole zone. And it's that correction which is the most important. And Jesse's done some analyses, again, using the carbon tracker model to evaluate how frequently we need to fly to beat that error down. So the red and blue dots are just that correction for the 45 times 10 to the 16th surface. That's the boundary between the 3rd and the 4th box, and then the 15 surface, which is the boundary between the 1st and 2nd box. And what you can see is that and then the shaded is the spread from taking this many flights per month from a whole bunch of different months. And so the span represented by the shading is large when you have when you don't have very many flights per month. So this is we had about 6.5 or 7 flights per month during our field season, so we were right about there. We'd like to get out to about 13 flights per month to beat those errors down a little bit more. We are correcting for them, but it still contributes to the ultimate precision. I think I have time to show one methane plot. I like to show this because it's something I don't understand. I'm hoping I'll eventually show it to somebody in the audience who will tell me what's going on. We saw this during orcas as well, this really cool thing that at high southern latitudes during summer, methane just marches down every day. So in the middle here, you see purple on the right, then blue, then green, then yellow, then red. That's just photochemistry eating methane away every day during summer. But 3 times on 3 different days, profiling over McMurdo, we saw these methane plumes shown in red and orange and green in the middle plot at low altitudes, and we don't know where those came from. I ran back trajectories, and they all came from they seem to come from 3 different places, and none of them from town. But I'm hoping to work with some people to run some higher resolution ones. One idea would be the waste treatment facility in McMurdo, but otherwise I have no good guesses. But there are things we could do with this data to get at the photochemistry, the reaction of OH and methane, and whether that OH, whether this loss rate is indicative of local production of OH or transport of low methane air from lower latitudes. And then finally, just operationally, I mentioned we chose this rack because it would avoid having to remove an entire pallet. So we're in the back of the plane. It's called pallet position 5. And so we're off to the side so they can still fly a pallet there. But something we found out quite late in the process, actually, after sort of 3 years after making the decision to go with this rack, is that they had to have a cutout on the rack, on the pallet in front of that rack for egress. So this is a pallet that's okay to fly there because it has this 14-inch cutout, and you could get past it if you needed to get to the exit in the back. On the right, there's a few more pallets forward in the plane that are typical of what they like to fly back in pallet 5 often. So it was possible they could plan somebody could plan to always have a cutout on that pallet in that position, but the people who plan the cargo are maxed out in terms of their time coordinating all of the cargo that needs to go everywhere on the ice. And so that was an additional complexity that was not, not supportable or not supportable with a lot of enthusiasm, I'll say. So as a result, we've been pursuing a different approach the next time we go. So we now have this instrument rack crate. So it's a crate with an instrument rack in it that I took out to the Air National Guard and tested. And we're planning to put it forwards in the cabin, which will have a much shorter inlet line run, which is great for us. And then it turns out that they always like to fly pallets in the back because they like an aft center of gravity for getting those skis off the snow. And they almost never fly a pallet in this forwardmost position because they generally run out of sort of useful load before they get there. So it turns out it's a lot better to displace an entire pallet at the front of the plane than it is to displace 14 inches of a pallet in the back of the plane, which we only learned by going there and testing all of these things out. This new rack is also easier to roll on and roll off. It might open some opportunities to sample from other aircraft as well. And the paperwork's been submitted to the Air Force, and we're awaiting approval. So the outlook is we're moving to that rack crate, and then the other big development is highlighted here by a Dear Colleague letter that NSF put out last June, just highlighting that, after essentially losing 2.5 years of field time because of COVID, that they're quite far behind in the science they want to support, and costs have gone up as well, so there are also financial issues. So as you can read here, due to these compounding constraints, the upcoming season will be significantly curtailed. So we were deferred. Charlie and I are not down there right now. We're here planning for next season instead. And we're hoping to fly our 3 full field seasons in 24, 25, 25, 26, and 26, 27. Just some quick conclusions here, restating what I already said. The aircraft is the best way to get at Southern Ocean CO2 exchange because it's less sensitive to the spatial heterogeneity and the vertical mixing biases and more sensitive to fluxes. The moist isentropic box model that Yuming developed and Jesse's adapted can provide robust flux estimates for multiple latitude bands and at monthly or sub-monthly resolution. The results from last season were comparable to the climatology, but with some interesting differences and comparable precision. And these LC-130s really provide the most cost-effective means of obtaining CO2 measurements at high southern latitudes. We've done some analyses of what it would take to get the G5 down there to do this, and although I would love to do that, it's a lot more. It would be a lot more expensive. So we're really hoping to continue to optimize this project. And then finally, thanks to the people who are out there in the field: Charlie, Eric Morgan, Hannah, and then Alex, Zoe, and Hugh. Thank you.
Thank you, Britt. We have time for questions in person and virtually. Tammy.
Thanks a lot, Britt. This was really very relevant and impactful work, and I applaud you for figuring out a way to get these observations even without the NSF aircraft. So good job there. My question is about the change in the SCARGO uptake estimates in the test flights that you recently did. So why, my question is it possible that it's due to just climate change impacts and that there's a trend and there's a decrease in the uptake because the Southern Ocean is simply not able to take all of our CO2 globally anymore?
Yeah, that's a great question and something we'd really love to answer. I think maybe you were alluding to this sort of in this particular region, we're now seeing less uptake than what we saw from this climatology. So that that would match up with, say, for example, an increase in the winds, bringing up more CO2 from the deep, or maybe warming, changing the stratification near the surface during summer. All of which are possible. I think we would need to measure sort of, again, for 3 years to really attribute a difference like that to a trend. But that's really the ultimate goal, because what I didn't show is if you run our system models forwards, they diverge quite a bit in terms of whether they think, the Southern Ocean right now is kind of providing this 10% discount to climate change. So I mentioned it's, 40% of the CO2 that we're emitting that's stored in the ocean is taken up in the Southern Ocean. About a quarter of what we're emitting is actually taken up by the global ocean. So 40% of a quarter is 10%. So 10% of what we're emitting is sort of being taken up there. And there's a natural outgassing that sort of goes in the opposite direction. So the uptake we measure is not 10% of the total. But anyways, it's providing this great service, and we want to know if it's going to continue.
Any more questions?
Thanks. Thank you very much, Britt. I was curious, what do you suspect is the big offset between the floats and the pH measurement versus your measurements?
So we're close colleagues with the people who are running that program, and we're still on good terms with them. But they haven't found a smoking gun yet. They have sort of acknowledged that their estimates might be biased high and that there are several possible reasons. One sort of, I guess, technicality is that if you look at their uncertainty estimate, uncertainty is still quite large on their PCO2 estimate. So by the time you take a pH measurement and then you convert it to PCO2, there are uncertainties that creep in owing to things like, understanding the reaction rates in the carbonate system and being able to estimate what the alkalinity is and other things. So their actual PCO2 numbers have sort of this, 7 to 10 parts per million uncertainty on them. So on the one hand, they can say, well, it's sort of maybe is, just at the outside edge of our, it's a 1 sigma, and this is sort of maybe on the outer edge of 2 sigma. But the other challenge is those floats are never calibrated. They are before they go out and deploy them, but then when they put them in the water, there's sort of this shock that happens as everything cools down, and they just, they sort of calibrate them against what they think the deep water signal should be, and it's not able to go back and catch one and see if it's drifting or anything. So it's very, from an observational or instrumentational point of view, it's very challenging to know for sure what's going on. There's now a lot of effort in looking at ship crossings where ships happen to go past where they are, and then there's a lot of noise in doing those comparisons, so you need many of them before you can pull out a signal. I don't know. I just having done a lot of measurements on aircraft and seeing that sometimes when you go up and then you go down, you get a different profile on the way up and on the way down, and the atmosphere shouldn't care whether you're going up and down. These instruments sit around for 2 weeks, nice and happy at I forget 2,000 meters, and then they pop up really fast. So if I was doing that with an airplane, I would worry about possible biases creeping in. So I think there's just more work to do.
So you showed a signal earlier on in the talk that you thought could be attributed to Pinatubo.
Oh yeah.
And I'm wondering if the climate intervention community is talking to you and asking you about what potential impacts could be of stratospheric aerosol injection.
Yeah, so there's a paper by Galen McKinley and Amanda Fay where they so this sort of thing here where it's going up and not down has been a feature that people have stared at for quite a while because, as I mentioned, it was sort of a lot was made of that back in 2007, and then there's sort of science and nature papers on the reinvigoration of the sink. So what they showed was that sort of this global cooling or warming less fast than you might have expected just impacted the solubility, and that impact caused CO2 uptake to just be not I might have a sign wrong on my explanation there. I might have to go back and reread that paper. But I think, so it's secondary to sort of the direct temperature. The impact of that change in CO2 sort of feeding back on the warming would be smaller than the direct effect from the aerosols. So I'm not sure if the geoengineering people are very focused on it, but it's a good point. I should bring it up in some of our discussions and see what people think.
So does the presence of the clouds affect the uptake and photosynthesis at all?
Well, yeah, it certainly would. The algae are driven by, photosynthetically active radiation, which is reduced with cloud cover. It also has implications for, a lot of our estimates, a lot of sort of scaling up techniques are based on satellite measurements or our understanding of, say, the biological processes is based on satellite measurements of chlorophyll, and you only get those when it's not cloudy. And as you know, the Southern Ocean is cloudy almost all the time. So we were flying around during orcas, it was, sort of 85% cloudy. So I think, this affects the measurements, but then it does affect. So if it got less cloudy, then you might expect the algae to grow more.
I just wondered if as anybody has segregated the data with respect to the amount of cloudiness to see whether there's a signal there.
Yeah, it's jogging something in my memory about the clouds and the impact on the CO2, but I'm not able to pull it up right now. So let me think about that and get back to you. I think it would be a cool thing to look at.
I have a question about you were talking about like the methane and that there were these bumps at these low levels of the methane, of your vertical profiles of methane. What levels were they at?
Yeah, so I will answer that question. I just remembered what I was trying to think of. So CESM gets, I think, not enough clouds. Somebody will have to jump in online and tell me I've got this wrong. Over the Southern Ocean, they also get, so the SSTs are all too high. So when we were trying to use CESM to predict what we were going to see during orcas, we were running into this issue that the SSTs weren't quite right and the clouds weren't quite right. But there was the thought that maybe that model was taking up too much CO2 because of that reason. I don't think we ever wrote any of that up. That was all just sort of the science team speculating. So yeah, you're going to tell me what this was, which will be great. So this one was 5,000 feet. It was while the plane was flying level. That's why it looks so sharp. It was, if you look at it versus time, it's this kind of bell-shaped plume, whereas the other two were while the plane was climbing up and down. So 5,000, 5,000, and 2,000 feet.
Do you have concurrent measurements of aerosols or water vapor or relative humidity?
We have water vapor. And I don't see anything unusual there. And we also have, of course, methane and CO2 and CO in this case. And nothing really jumped out. And so, if it was, around here, if you see methane go up, you usually see CO go up with it. I haven't really thought through what the emission profile of McMurdo would look like, but I would have expected CO2 to go up and didn't see it.
Well, we're a little past our seminar time, so we'd like to thank our speaker for talking about the SCARGO program, and I hope that him and Charlie and some of his colleagues and staff get to go out there next winter. So let's thank our speaker.
Thank you.